Okay, so let us start our lecture. So this is going to be our fourth lecture on power system operation and control. So last lecture we saw about structure of power systems. We saw a few basic characteristics. We saw the primary equipments. What all equipments are there? Main equipments across these transmission, sub-transmission, and distribution systems. We also saw the transformation of a vertically integrated utility to a liberalized electrical systems. So this all we saw in our previous lecture, and we also saw that how what all in a broad sense what all things change from vertically integrated systems to liberalized electricity systems. Now, we also saw some advantages and features for interconnected power systems, why we go for interconnection. So these all we have already seen, and lastly we saw about the structure of Indian grid, how does it look like, and what is the installed capacity and the peak demand of Indian grid. Now, moving ahead from here, we will be discussing about the control in power system. So, can anybody tell me what exactly we want to control in power system? What is the essential commodity which we want to control? Good, good. Yes, we want. Yeah, yeah, good. Yeah, frequency and voltage. That is the prime thing which we want to ensure. If as a consumer if at my home, if I'm getting a constant specified rated voltage and a rated frequency, I'm happy, right? Because why I am happy? Because all the appliances what we have at our home, they work at a rated voltage and a rated frequency. If we work at that rated voltage and frequency, then the life of those appliances increases. And if we, let's say, if we get a poor voltage, poor voltage means either high voltage and the low voltage both comes under as a poor category. Also, if we get frequency which is not in the rated band but it is increased, we are getting higher frequency or a lower frequency. In both cases, our appliances, the life of appliances actually keeps on reducing. So that's why we want the voltage and the frequency to be supplied at a rated value. So just to give you a quick background, that we always convert into electrical energy from either from heat, light, or mechanical energy. Why we convert it? Because it is easy to transfer or transport. It is highly efficient and reliable. So for example, if you can imagine a world without an electrical system, then let's say if you want to consume or if you want to use any appliance like even our refrigerator or air conditioner, we have to generate electricity at our local end, which is not always possible. So therefore, and for any other activities, either you want to heat anything, either you want to run a motor, you need electricity, and it is efficient to generate electricity in bulk. So that's why people generate electricity in bulk and transfer or transport electricity, and it is obviously efficient and reliable. Now, for a properly designed power system, we need some fundamental requirements. Can you guess what all fundamental requirements are there? Anybody? Okay, let me give you one fundamental requirement, probably others you can guess. So one is obviously we want our load and generation to be balanced, because load, either the active power demand or the reactive power demand, it is continuously changing over a day. We want the generation should be equal to the load. Why do we want generation to be equal to the load? Good, yes, exactly. So we want to maintain frequency at 50 Hz, and that is only possible if generation is equal to the demand. If there is any disturbance, the frequency will deviate from 50 Hz, and this we are going to see in the course later on in detail how exactly everything happens. So still we are in the introduction phase, so yeah, just bear with me. Any other requirement, fundamental requirement for from a power system? Yeah, good. That is there. Voltage should be at a nominal value. Frequency should be at a nominal value. So that is there. But also there are few others. So yeah, huh? Location. Location. What exactly do you mean by location? So location, instead of location, you can think even further. We want to see, because location, I think what you mean here is that the load has to be connected from the grid, one thing. And also we need to ensure, let's say if some contingency takes place, then in that case we are still able to satisfy the demand or satisfy the load. So in that case, what we need, that is the another criteria, important criteria, is reserve. We need spinning reserve. So, so we need the spinning reserve. This is required in case of any contingency or any unbalance which is happening, or any, because obviously we cannot predict lot of things in power system. So obviously power system is always varying. So and specifically if contingency happens, contingency means any fault has taken place either at the on the transmission lines or at the generators, we need to supply that excess generation or shortage whatever is happened. So for this, spinning reserve is required. And why spinning reserve is required? Because we cannot store electricity, right? So as we cannot store electricity, it has to be uh, generated whenever it is needed. So therefore you have to be ready whenever a shortage is there, or a contingency has taken place, or a fault has taken place. You have to be ready to provide that spinning reserve. Now another important criteria is the energy should be available at minimum cost. It should be economical. We should not supply electricity at at expensive rate. For example, you can easily imagine that we have various type of power plants, like thermal power plants. In thermal, we have coal, diesel, gas. We have nuclear, we have renewables. And if, let's say, if we only, because you can think of that many at many places we have nuclears which are abundantly available at many places. Also we have diesel and gas, which is at the time at this time we have available in plenty, but obviously it is day by day depleting. But yes, at this moment we have in plenty. So why we cannot generate by using all those costlier or expensive raw material? Because if we generate at a costlier or expensive raw material, then the same price has to be passed on to the customer. So eventually the cost or the price of electricity at the customer end will also increase. So therefore we want the supply should be at minimum cost. Right, and also these days another important concern has came into existence, that is ecological impact. Ecological means because if you have, let's say, coal based power plant or diesel based or gas based, even nuclear, you those type of power plants, they after the use of their raw material, there is some byproduct, and that byproduct is either in terms of gas, or because you are burning something, or either you can say that there is some byproduct which is coming out of after the burning. So those are basically not eco-friendly, so we have to take care of that. So therefore we have to consider that, okay, we need to ensure that there are less emission in that sense, or ecological impact in that sense. So these are the new factors which are coming up, but earlier people did not focus on this, but these days, yes, they are considering all these factors. And lastly, quality of power supply must meet certain minimum standards, which one of you have already told, that the frequency has to be constant at a rated value, the voltage has to be constant at a rated value, and also in addition there has to be some level of reliability. We cannot say that, okay, you will means you cannot say that any time it is like power is not available. So you have to have some sense of reliability, that yes, my power is or electricity is going to be available whole day. So there has to be a level of reliability for that sense, and that will automatically come if you have spinning reserve sufficiently available with you, and sufficient level of protection you have taken care. So then you have that level of reliability which you get automatically. So these are some of the fundamental requirements for which we have to take care for designing and operating a power system. Now let us dive deeper into it and see few more constraints or criteria what we need to for managing this power system. So basically you see in broad sense, I've just taken this figure from a book. Here you can see there are three main blocks which we need to ensure. One is generating unit control, which is controls of a generator. You have a system generation control, which is basically how system is controlled across all the generators. So you can, one generator is here, one generator is here, one generator is here, there can be few more generators. All generators you can control at a central level, right? And also you have few transmission controls. So these three are broadly the main controls of a power system, which will ensure eventually the frequency and voltage is at rated value. So for this, let us see quickly briefly how each of these controls works. So specifically, if you see in the generating unit controls, which is generation control, here you broadly see there are two main controls, which is prime mover control and excitation system control. So just by the name, and I'm sure you must have studied some part of it in your bachelor's degree, but prime mover control basically ensures the frequency as well as the power balance, or rather I could say that the real power or the active power which is generated by a generator is mostly controlled by prime mover movement, and this prime mover control also ensures the frequency, because the frequency is kind of dependent on the synchronous speed at which it is rotating. So that prime mover control will take care of that, and that is done by the shaft power. Basically, you have to give power to the turbine or the shaft at which it is connected. Also, the next is excitation system control. Here you basically ensure that the voltage what a generator is setting at its bus or wherever the generator is connected, that voltage is controlled or set at a particular value, and that value is controlled by excitation system, and this is done by increasing the field current of the generator, right? So yeah, this is in broad. I've written that here, so for your reference you can easily see that. Also in the system generation control here, as I told you that here you ensure that all the generators which are available in a system, they are generating a specified value what it has been told to generate in the day ahead manner. So here they try to balance the complete generation and demand across the network, as well as including the effect of losses. This is also important, and eventually when the generation and demand including the effect of losses is balanced, then the desired frequency is achieved, and this all is taken care by the system generation control. Here you have tie flows also, where if there are two different systems which are connected via tie line, those tie flows will also be the power at these tie flows will also be maintained. And the next is transmission control. Here in the transmission control, you have mostly the reactor power and the voltage control. Here you have a lot of devices which are connected in the transmission system. For example, capacitor banks, reactor banks, static power compensators, UPFC, all those things. You also have HVDC transmission system. So using all those things, you can control the voltage and set the voltage at a specified value without even controlling or disturbing the generating unit controls. So just by controlling the transmission controls, you can still control some of the voltages across the network. You have few phase shifting transformers which can also help in controlling these voltages. You have tap changing transformers which can also help you in controlling the voltages. So basically all these control what I have told you, they actually contribute in two sense. One is they eventually try to maintain the voltage and frequency at a specified at a rated value, as well as ensure that all the parameters or the variables which you can control, they are operating within their acceptable limits. Acceptable limits is important. We cannot, like for as a transformer, we cannot tell the transformer to tap at any ratio of voltage. There is some limit or some bound on that transformer, so that is ensured at every level or at every time instance whenever you are controlling this power system. Also, this is also important that whenever a disturbance takes place in a power system, during that disturbance, whatever is the dynamic performance of the power system, that dynamic performance should be stable. It should not, the disturbance should be, means the power system should be able to sustain that disturbance and maintain the power system into stability, means maintain the stability of the power system. So these two are the major controls where this power control of different components or variables or equipments connected across the network, we can control those things eventually to arrive at this stable value of voltage and frequency. Now coming to the timeline sense. So again, so whenever a disturbance takes place, let's say a small disturbance has taken place, the first step or the first equipment which actually sense that disturbance is the protection devices. They work at a very high speed. and they ensure that the power system or any disturbance will not damage the power system equipment. So therefore the first step, what whenever a disturbance takes place, the protection kicks in immediately. And then immediately after that the voltage control kicks in. So if either the generators or at the transmission level, the voltages are set to improve, or we try to disturb or improve the quality of voltage. And then after that the turbine control kicks in. So turbine control means it actually tries to balance the frequency. So the next kick in part is frequency, where frequency is tried to stabilize and brought back to the rated value, which is 50 hertz for us. And even then, if that is not as happening, so then we will go for tie line power for further controlling of the frequency. And there are few more things as per the time. If time is more, then we can go for a small reserve. Here the reserve can be there. Then we can have a small market, which can, or like real-time market, which can actually help the power system to economically decide which generator has to contribute. If you have more time, then you can have intraday market. There is also a concept of intraday market which can actually take place here. And then if you have, let's say, a day ahead, if you are coming, then you can have a day ahead market, where you can have a unit commitment and you can tell a generator when to generate during a day. So all these things, I'm increasing the timeline here as I'm going on top, but instantaneously protection takes place first, then voltage control, turbine control, and tie line power and frequency control. So these things kick in at different time intervals, and we are going to discuss all these in detail during the course. So this is just a startup, that's why I'm giving you a brief introduction here, but yeah, things will be covered in detail later on. Also, obviously, as you can see from here, there are variety of controls. They depend on different time scales, at what time we want to control or signal has to be communicated, and also it depends on the location from where we are giving that signal. So location also plays a bigger role. This again we will see later on in the course as we move on. Also just wanted to give you a quick heads up, although I mentioned voltage and frequency controller here, but they are in a way linked, they are cross coupled. So we obviously, you must have observed in fast decoupled load flow, what you must have studied in your bachelor's course, that voltage is decoupled from the angle. Voltage magnitude is decoupled from the angle based on P and Q. So that is there, but still power system is everything is coupled and everything is connected. So they are kind of in a nested loop. So if you disturb one, the other will also get disturbed, but magnitude of disturbance might be different at different time intervals and at different locations. But all these things we are going to see later, and just this is for your heads up. So if, let's say, we'll see a hierarchical structure of control actions, what is taken in the power system. So if, let's say, assume that everything is working fine right now, whatever is the load is equal to the generation plus losses. The frequency is at 50 hertz, the voltage is at nominal value, everything is fine right now. Now what happens, the first thing is this load. This load is not at all controlled. We never think before switching on our tube light, fan, air conditioners, any appliance whatever we are using, we never think of that switching on before that. So we always whenever we want we switch it on, whenever we want we switch it off. So it is not at all controlled. So whenever some load disturbance or load change has happened, I won't call it as disturbance, it can be load change also. So whenever a load change has happened, this can also happen because of some fault or a line outage, a transmission line outage, due to which the loads connected at the downstream of that line, they went into blackout or they went into load shedding. So there can be many reasons for this load being disturbed or changed. So let's say this load change has taken place, and then this load change is observed at the control center due to we have lot of SCADA systems installed across the network, which actually communicate all the signals, measurement signals, to the control center, and then using that measurement signals, control center takes some actions. So we will be seeing SCADA systems in brief towards the end of this course. So it is going to be probably the last 1 or 2 lectures. We'll be looking briefly on these SCADA systems. So SCADA, using the SCADA systems, these signals are being communicated at the control center, and then control system performs some of the applications, power system applications like state estimation. These things you are going to anyway see in the power system analysis course. Power flow control, state estimation. It can also perform economic dispatch, security assessment. So we'll be seeing some of these in this course as well, and some of these you will be seeing in power system analysis course. So these studies are performed at the control center, and then control center again gives back a control action to either to the generator or a transmission or distribution system. If the signal is going to the generation, it can be for the turbine control or voltage control. It depends on the level of disturbance happened at the load side, or if it is if the level is enough to control, which can be controlled by a transmission or distribution system. It can be either tap changer control, reactive power compensation, maybe setting or changing the settings of HVDC and FACT devices. So these controls can play, this is the way a control action, or whenever a disturbance takes place, how these control actions is taken care by the system operator, either by communicating it to the generation systems or the transmission and distribution systems. Now this is a very exciting picture. I really like this picture. Just to give you a quick idea about the frequency control. Like I was telling you before, one of you already told that we need to balance the generation and demand, and because if the generation and demand is balanced, that means the frequency is at a rated value. So this rated value frequency you can see from here. Let's assume there are few cars which are connected to a big giant wheel, and every car, let's assume there are different length of the strings by which these cars are connected to this giant wheel, and then there can be different speed at which all these cars can move. They can have of different capability. You can imagine this from in the context of the power system. You can imagine that these are different type of generators which are connected. Now all these cars are trying to pull this giant wheel. Either they might be moving in a uphill way, so let's assume that they are going uphill, or they can go downhill also. So if let's say they are going uphill, that means this wheel, whatever is the speed of this car or power of this car, this wheel will always move at a constant speed, at a unique constant speed, and it depends on, let's say if it is moving uphill, that means the speed will be low, and all the cars will be like trying to push this wheel up, and whatever is the speed of this wheel, you can call it as that frequency of that wheel. Or if let's say if you are maintaining it as 50 kilometers per hour, then you can say it is moving at 50 hertz. And if let's say if this wheel is we are taking this wheel to downhill, then probably these cars does not have to do much of an effort, and then wheel can take a gradual speed on its own. So this happens when load is kind of reducing. In the power system context, in that case the generation can reduce down gradually, and then the frequency will be maintained, and in the uphill everything will be reversed. So this is a very interesting picture to visualize the frequency, how we maintain this at 50 hertz. And there are obviously various n number of generators connected across the network. Right. If you have any queries till here, I can answer those queries. So we can stop here now.